Let's take a look at an example of mass defect for the nuclear reaction in the first atomic bomb. That would be this one here, where uranium-235 splits into two nuclides and some neutrons. So let me write that down in a bit more detail. Okay. Uranium-235. So this would be an example of nuclear fission. Uranium-235. That's 92 protons. Now when a slow neutron comes into contact with the uranium-235 nucleus, they will stick together and become so unstable that it will split into a number of fragments. Now one is a much smaller nuclide of barium, and the other one is also a much smaller nuclide, krypton 92, and it will also produce 3 more neutrons. Right. Of course, in this case, the total number of protons and neutrons remain the same after the reaction. And as well as these products, it will release an amount of energy in the form of kinetic energy of these products. It will release, I'll just add it in here, 205.5 mega electron volts. So one nuclide of uranium-235 would release this amount of energy. Now let me look at 2 questions. Now the first one I want to talk about is this. If you might have read about the amount of energy given out by an atomic bomb. If you have read about it, you might have heard or read things like how an atomic bomb can release many tons, the equivalent of many tons of TNT of energy. Right? TNT is dynamite. And the first atomic bomb, actually, the first atomic bomb, if you look this up in Wikipedia, released about 20,000 tons of TNT of energy. Okay, release the equivalent of this weight of TNT of energy. So that's a huge amount of energy for a single bomb. Now, given this value, right, given this value, I would like to work out two things. First, I would like to work out the mass equivalent of this amount of energy. So what mass is needed? Okay, let me be a bit more precise. What mass is converted to energy? Okay, the next question is, what mass of the uranium 235 is now let's see, is fissioned? I was going to say is used, but I'm not exactly sure if the efficiency is 100%, although it might be. So I'll just say exactly what mass of uranium 235 has to be split in order to produce this amount of energy. So based on the information given, right, from this equation, from the amount of energy released for a single splitting of the uranium nuclide, and from this information about the amount of energy given out by a bomb, let's try and calculate the answer to these two questions. Now there is actually one more piece of information that we need, and that is exactly how much energy is 1 ton of TNT. Now 1 ton of TNT is nowadays used as a kind of a unit of energy, and it is defined to be equal to 4.184 gigajoules. So this is the value that we need to use. Okay, so let's start with the first one. Now the first one should be fairly straightforward, at least more straightforward than the second one. We need to make use of E equals to mc squared. So since we know E, or at least we can get it from here, we can find the mass. Okay. Right. So let me clear this up and to work this out. Okay, so we have E equals to mc squared. Now we want to find the mass that is converted into the energy. So m is equal to E over c squared. I need to know what E is. So let's recall what information we have. We have 20,000 tons TNT equivalent, and for 1 ton of TNT it's 4.184 gigajoule. So therefore the corresponding energy should be equal to, let's see, okay, 20,000 times 4.184 times giga is 10 to the power of 9 joules. So this is E. Okay, and we know C is speed of light, 2.998 or approximately 3 times 10 to the power of 8 meters per second. So putting these two numbers into the equation and using our calculator, this is what I found: 0.00093 kilogram. Now that's approximately equal to 1 gram. 1 gram. How much is 1 gram? Now, if you'd like an idea of how much is 1 gram, it's roughly the weight of a small piece of paper. Maybe a piece of paper about the size of your hand, or a dollar note. So this is the amount of mass, 1 gram, that's needed to produce this okay, again, needed, to be careful about when I say needed, because it could mean the actual mass of the whole bomb that's used. But 1 gram is the mass that has to be converted to energy to produce this 20,000 tons TNT equivalent of destruction. Okay, so that's a very scary prospect. So roughly a piece of paper. Right. The next part of the question that I want to look at is how much uranium we need to use. Okay. Now, if you recall the equation, it went something like this, right? It went something like you have a neutron plus uranium 235 becomes a barium, a nuclide, a krypton nuclide, 3 neutrons, and this amount of energy. Let's see, right, 205.5 MeV. Okay, so given now that we know both the energy and the mass equivalent. Okay, we have all these values. We want to find the actual mass of uranium that was fissioned to produce that amount of energy. So this equation tells us that the fission of 1 uranium atom produces this amount of energy. So the question is, if this amount of energy is produced, what's the mass of uranium that fissioned? So what we could do is this: if I divide this total energy by the energy from one atom, I would get the number of atoms that is fissioned. And then if I can find the mass of each atom, I can calculate the total mass. So that's the plan. So let's see. If I call this energy, I'll just give it a name, maybe X. Maybe not X, maybe E1. So if I divide this by this, if I divide E by E1, I know that I can get the number of the uranium atoms. Okay. Then if I want to find the mass of the uranium atoms, I can multiply this by the mass of each atom. The mass of each atom is 235 times the atomic mass units times U. Okay, so that would be the mass of one uranium 235. Okay, so let me write this out in full. 235 times U. So U is the atomic mass unit, which is 1.66 times 10 to the power of minus 27 kilogram. Okay, and E, we already know from there, 20,000 times 4.184 10 to the power of 9 joules. Okay, and that one, energy produced by the fission of one atom, that's 205.5. Now we need to convert MeV to joules. So M is 1 million 10 power of 6, and E is the electronic charge, 1.6 times 10 to the power of minus 19. So that would give us the MeV in joules. So we're all set, lots of numbers, but once we multiply this out, we'll get our answer. And I did that and got, see what I got. Right, I got 0.99 kilogram. So this is the actual amount of uranium that that was fissioned, that has to be fissioned in order to produce this 20,000 ton TNT of explosion. Alright, just about 1 kilogram of the uranium 235.